Okay, here's part 2 of section 5.3. We're going to finish example number 1, E and F, and then maybe even do example number 2. So we've been talking about the fundamental theorem of calculus, where we're integrating from A to B. And so if you look at example number 1E, it asks us to integrate from 3 to 6 of dx over x. I don't know about you, but I'd like to take that dx and move it off to the side. So the first thing I did is I rewrote my problem so that it says 1 over x dx, the integral from 3 to 6. And so if I bring up that x and I call it x to the negative 1, and then I use my power rule for integration and I add 1 to the exponent. Uh-oh, I hope you caught me. You should never be dividing by 0, right? And so do you remember the integration rule for 1 over x? Don't ever divide by 0. Remember that the antiderivative of 1 over x is the natural log of x. Natural log of x from 3 to 6. That means I can plug in my upper limit, I can plug in my lower limit, and I can evaluate. So I have the natural log of 6 minus the natural log of 3. And you remember our log rules where if we have 2 different log problems, we can actually condense it, or if we have 1 log problem, we can expand it? Well, that's what I'm going to do here. I'm going to take these 2 log problems that are being subtracted, and I'm going to condense it into 1 log problem. Remember that subtraction, when I condense it, turns into division. So I end up getting a natural log of 6 divided by 3. And so I could really say that my final answer is the natural log of 2, whatever that decimal is if they ask me for a decimal. So that's the area underneath my curve from 3 to 6. Look at example number 1F with me now. It's a little more complicated. Remember that there is no such thing as product rule, there is no such thing as quotient rule, and there is no such thing as chain rule with antiderivatives. So don't try to do a quotient rule here. Hopefully you can somehow rewrite this original problem into a form that we do have a rule for. So pause the video, try to rewrite it, and see if you get the same answer as me. I separated it into 2 different fractions, each with their own denominator instead of a common denominator. I then reduced, and I ended up getting an integral of from 1 to 2 of 1 over v plus 3v squared. Because they're only separated by a plus or minus sign now, I should be able to integrate each piece separately. I should be able to integrate this piece, I should be able to integrate this piece, and then evaluate it from 1 to 2. So the antiderivative of 1 over v, or 1 over x, remember, is the natural log of v. I can use my power rule and add 1 to the exponent and divide by that new exponent. So for the second piece, I ended up getting a v cubed. Using my fundamental theorem of calculus, I can plug in my upper limit, my 2. I can plug in my lower limit of 1, and then I can subtract the 2. Now be careful when you have multiple terms. I don't know if you've noticed, but I've put a big old parentheses around both of these pieces because I want to make sure that this negative sign gets distributed to both pieces. Or do the whole chunk and then you can subtract it. But just be careful that if you have multiple terms in that second part, that you distribute the negative through. Okay, that's a common mistake I see students make. I noticed that I had natural logs in both of them. I have a natural log of 2 minus the natural log of 1. I actually condensed that using my log rules and really said that I have natural log of 2 divided by 1, which is just natural log of 2. And then 8 minus 1 is 7. So I have a natural log of 2 plus 7. I could put that in my calculator if I needed to, round it if I needed to, if WebAssign asks, but the exact area underneath the curve of this function from 1 to 2 is natural log of 2 plus 7. All right, let's do example number 2 also in this video. And then the last thing we'll talk about in this unit is the second part to our fundamental theorem of calculus. But here's example number 2. It asks us to find the area of the region bounded by the graph of y equals 2x squared minus 3x plus 2, the x-axis, and the vertical lines x equals 0 and x equals 2. I have some sort of a parabola. I have the x-axis, and I have 2 vertical lines, x equals 0 and x equals 2. I don't know about you, but it kind of helps me draw a picture to visualize what's going on, so that's what I did. I knew I had some sort of parabola. I have the x-axis, I have a vertical line x equals 0, I have a vertical line x equals 0, x equals 2, and so what I'm really finding is the area between all of those pieces. I'm trying to integrate my function, my 2x squared minus 3x plus 2, from 0 to 2. So I was able to rewrite this into an integration problem finding the area underneath the curve from 0 to 2. Now I can integrate it. I can use my fundamental theorem of calculus to plug in my upper limit minus my lower limit. I ended up getting 16 over 3 minus 2, so I got a common denominator, and so I ended up getting 10 over 3 as the area underneath my curve from 0 to 2. And so they might give you an integration problem as is, or they might give it to you in a little bit of a different form and ask you to find the area bound by a couple of different pieces. That really just means the same thing. You're just integrating it from A to B using our fundamental theorem of calculus.